Hello. Today we're going to talk about measurements and the international system of units. So, when we talk about measurements, measurements have to have two components. They have to have a number and they have to have units. Measurements without units don't mean anything. So, as an example, your teacher is 170. Well, 170 what? 170 pounds, 170 years. Without units, a measurement is meaningless. So here are the international system of units. So length is in meters, mass is in kilograms, time is in seconds, temperature is in Kelvin, electric current is in amperes, amount of the substance is in terms of moles, and we're going to talk a lot about this unit in this particular semester. And luminous intensity is in terms of candelas. Okay, and that's all we need to know. Every other unit is derived from these seven. So let's look at the derived unit for density. Okay, our equation for density is mass divided by volume. Or we could say that density of a substance is the ratio of the mass of that sample in its given volume. The units are kilograms per cubic meter. That's the mass divided by the volume. Now, commonly when we talk about solids, we talk about them in terms of grams per cubic centimeter, or for gases, grams per liter. But any of these derived units are your mass divided by your volume. So let's say that we take some water and vegetable oil and kerosene and put them into a test tube. These three substances don't mix together, but they will layer one liquid on top of the other. And if we're asked which substance has the lowest density, our answer would be the kerosene, because substances that are less dense float on substances that are more dense. So another example might be if we had a beaker of mercury and we had a copper penny. Copper and mercury don't mix together, but the copper penny would float on top of the mercury. So if our question is which metal has a lower density, it would be the copper because it floats on top of the mercury. Okay, so if we look at a problem, it says a sample of lead sulfide weighs 12.4 grams and has a volume of 1.64 cubic centimeters. What's the density for lead sulfide? So density equals mass divided by volume. So we would plug in 12.4 grams for our mass, 1.64 cubic centimeters for our volume, use our calculator, and we get 7.5609 for our answer. We would round that to 7.56 grams per cubic centimeter. So looking at another example, when a 32.7 gram piece of chromium metal is placed into a graduated cylinder containing 25.0 milliliters of water, the water level rose to 29.6 milliliters. Calculate the density of chromium. So density equals mass divided by volume. Our mass is given to us as 32.7 grams. The volume is going to be calculated by taking the difference between the initial volume, which is 25.0 milliliters, and the final volume, which is 29.6 milliliters. And we get a density of 7.1 grams per milliliter. Now, how do we determine where to round off calculated values? It has to do with how the measurements are made and the uncertainty of those digits. So when we talk about absolute numbers, counting numbers are absolute numbers. Like when we say there are 3 atoms in H2O, that's a counting number. Or if we were to say how many people are in a particular room, that's a counting number. It's an absolute number. Okay, definitions are absolute numbers. Okay, saying 60 seconds in 1 minute, or 10 dimes in $1, or 12 in a dozen. These are all collectively called absolute numbers. Now, when we make measurements, we're going to have what are called uncertain numbers. So if we have a steel rod and we want to measure the length of that steel rod with a ruler, we would see that the length is somewhere between 9.1 and 9.2 centimeters. So we would record that value as 9.12 centimeters. The 9.1 are the certain digits. The 2 is the uncertain digit or the estimated digit, which tells us where between 9.1 and 9.2 that length would be. So let's look at a beaker that contains some liquid. And if we look, the level of the liquid is between 40 and 50 milliliters. So we would say that the 4 is our certain digit and the 3 is the uncertain digit, our estimation of where we think that level is between 40 and 50 milliliters. So looking at another example, we have a graduated cylinder and the level of the liquid is between 21 and 22 milliliters. We want to estimate where we think it is between 21 and 22. So our certain digits would be the 2 and the 1, and our estimated digit would be the 0.6. We definitely know the volume is between 21 and 22, and the 0.6 tells us where we think it is in between those two values. So here's another graduated cylinder. We've got markings for every 10 milliliters. We've got markings here for every 1 milliliter. And if we look at a close-up, we're going to be able to read the ones place and we're going to estimate to the tenths place. So we would say the 43 is our certain digits. The 0 would be our uncertain digit or our estimated digit. Okay, one more example. We've got a graduated cylinder. We've got markings for every 1 milliliter. And then we've got markings for every tenth of a milliliter. So when we go to make our measurements, the 2.2, those are the certain digits. It's somewhere between 2.2 and 2.3 milliliters. The 9 is our estimated or our uncertain digit of where we think that measurement is between 2.2 and 2.3 milliliters. Now, if we're given a number on paper, we need to determine the number of significant digits. So non-zero digits are always significant, meaning they're measured values, but zeros may or may not be significant. Now, if a 0 is what we call a captive 0, that means it's in between two non-zero digits, it's always significant. If the 0 is what we call a leading 0, meaning it's at the beginning of the number, it's never significant. And if we have what we call trailing zeros, meaning zeros at the end of the number, they will only be significant if there's a decimal point somewhere in the number. So if we look at these examples, if we've got 38.7 grams, these are all non-zero values. So they're all significant. There are 3 significant digits. If we look at this number, 2 times 10 to the 18th, this is really a 2 followed by 18 zeros, but those zeros are insignificant values. So this number only has 1 significant digit in it. If we look at our next number, really the only thing we have to be concerned about are the zeros. These are captive zeros. They're always significant, so we've got 7 significant digits here. Here, we've got a 0, but it's a trailing 0. We have to decide whether it's significant or not. And if there's a decimal point present somewhere in the number, this 0 becomes significant. So we've got 6 significant digits here. Okay, this number here, these zeros are leading zeros. They are never significant digits. So this value has 3 significant digits in it. Okay, this value has a trailing 0, which may or may not be significant. Because there's a decimal point in the number, it is. So this has 3 significant digits. For this number, these zeros are leading zeros. They are never significant. These zeros are trailing zeros. They will be significant if there's a decimal point present, and there is. So the 1, 4, and 0, 0 are all significant digits, leaving us with 4 significant digits. So now we're going to use significant digits in calculations. If we multiply and divide, we round the result to the same number of digits as the number with the least number of significant digits. So as an example, if we have 1.0, which has 2 significant digits in it, and we multiply it by 2.546, which has 4 significant digits, we're going to round our answer to 2 significant digits. Now, this 4 and this 6 that are written as subscripts, we're just going to carry these 2 significant digits along through our calculation, but in the end, we would round our answer to 2 significant digits. Adding and subtracting have their own set of rules. So if we add or subtract, we would round the result to the same number of decimal places as the number with the least number of decimal places. So as an example, if we have 1.0023 and we add 4.383, the calculator tells us 5.3852 is our answer, 3 is our answer. But because we only have 3 decimal places here, we're going to round to 3 decimal places here. If we have 486 and we're going to subtract 421.23, the calculator says the answer is 64.77. But because we don't have any decimal places in this number, we're going to round to no decimal places in our answer. Now, for rounding rules, we're going to use our regular math rounding rules. So if the digit after the digit we want to round to is less than 5, we're going to round down. If it's equal to or greater than 5, we're going to round up. So let's look at a couple of examples. We have 62.8 meters times 34 meters. The calculator tells us the answer is 2,135.2 meters squared. But there are 3 significant digits here and 2 significant digits here. We're going to round to the smallest number of significant digits, which is 2. You could write the answer as 2,100, but it's better to write it in scientific notation. So 2.1 times 10 to the third meters squared. Now, this is an adding problem, so we would want to look at the number of decimal places to figure out where we're going to round. 3 decimal places here, 4 decimal places here, 3 decimal places here. The least number of decimal places is 3, so we're going to round to 3 decimal places. And because the next digit is a 6, we're going to use our rounding rules and round this 5 up. Now, C is a multiplying problem. So we have 2 significant digits here, 2 significant digits here, 4 significant digits here. We're going to want to round to 2 significant digits. So we would get 6.5 times 10 to the third, or 6,500 if you wanted to write it that way. But again, scientific notation is a better way to go. So 6.5 times 10 to the third cubic centimeters. D, that's a subtracting problem. So we want to focus on the number of decimal places. The calculator says our answer is 14.23 kilograms, but there are no decimal places here. So we're going to want to round to no decimal places here. Now, this problem has two different steps. We would subtract first, and then we would divide that answer. And the calculator would say 0.85959%. But because this operation here leaves us with only one decimal place, we're going to round our answer to just one decimal place. Now let's look at a couple of more complicated types of problems. And we want to break it down and use our PEMDAS rules in order to come up with our answer with the right number of significant digits. So the first thing we're going to want to do is focus on inside the parentheses, and that's a subtraction operation. So 3.092 minus 3.07 gives us 0.022. Now, we're only going to want to round to the 100th place, but we're going to carry this extra significant digit through our calculation and then round off at the end. So we kind of just want to remember that this answer here leaves us with one significant figure. So we simplify the problem a little bit. Now it's just a multiplying and dividing problem. So, oh no, we have a subtraction here, sorry. So we've got 5.096 minus 2.1. Again, the least amount of decimal places is one decimal place. So really we would round this to one decimal place, but we're going to carry an extra couple significant digits until we get to our final answer. So we want to remember that this operation gives us two significant figures. We're going to plug 2.31 times 10 to the minus 4 times 0.022 divided by 2.996. Our calculator gives us 1.696 times 10 to the minus 6 for an answer. But because we only have one significant digit here, we're really going to round our answer to one significant digit. So 2 times 10 to the minus 6 would be our answer. So let's look at one more problem. Again, we want to focus on what's happening inside the parentheses first, and then we'll look at the total answer. So we're going to start here inside our parentheses, and I kind of pulled it out down here. So we've got 1.23 times 10 to the minus 1 minus 8.79 times 10 to the minus 2. Now, these are different exponents, so it's better to see the number of decimal places by writing them in ordinary notation. So 0.123 minus 0.0879, okay, we've got 3 decimal places here, 4 decimal places here. We want to round our answer to 3 decimal places. But we're going to carry an extra significant digit until we're done with our problem. So we'll take 2.09 times 10 to the minus 3, multiply it by 3.51 times 10 to the minus 2, divide it by 1.53 times 10 to the minus 5, and we get 4.795 in the calculator. But again, because we ended up with only two significant digits here, we're going to round our answer to 2 significant digits. So we would round it to 4.8. And that's the end of this lesson on measurements and international units.